Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 46. So in the last class, we were looking at connecting the Einstein coefficients with the transition moment integral, right? And that also with the intensities of the spectral lines obtained. Okay, so in this class, we shall start with continuing more about the intensities of spectral lines obtained. Okay, right? So intensities of spectral lines, especially in the context of astrochemistry. Now, so if you notice it, right, for the last two lectures, or in fact of quite a few lectures, our analysis was based on a lot of quantum mechanics. The transition moment integral was all based on quantum mechanics, and the Einstein's coefficients, the derivation of the Einstein coefficient, the relationship between them, etc., were all derived using some model, using some physics model. Okay, right? Now, in addition to all these models, which involve some sort of a theoretical basis or another, right? We can always study intensities of the spectral lines in an entirely empirical way. So the intensities, or intensity denoted by I, right, can also be studied empirically. I mean, what I've written here is empirically. The handwriting may be bad because it's the bottom part of the board. Can also be studied empirically. Okay, right? Now, what does empirical mean? Empirical means, without having any basis or any model or theory or any hypothesis-based model, right? Instead, the phrase empirical simply refers to the idea that, let me just go and perform some experiment and let me just, see the trends obtained. Let me see the trends obtained and let me see if there is any correlation based on the data, and based on the correlation or any trends in the data obtained, may I, try to come up with any inference. Okay. In other words, an empirical idea does not involve any prior theory or modeling. Okay, that's the basis of empirical modeling. So now, in the context of intensities of spectral line, while studying astrochemistry, people have found, okay, right? When I say people, a lot of astronomers over the years, okay, right? In fact, over the decades, have found that, right, let's say that there is some intensity of light. There is some intensity of light which is absorbed by some molecular cloud. Okay, let's say that let I be the intensity, or let's call it I naught. Okay, right? So let's call I naught as the intensity of the light absorbed by some molecular cloud, right? And let I be the intensity of the light emitted overall. Okay, let I be the intensity of the light emitted back. Now, let me ask you a quick question. Consider the ratio of I by I naught. Okay, right? Let's say, or you can consider the ratio of I naught by I. Okay, right? if you consider the ratio of I naught by I, now do you expect this ratio to be greater than 1? So the question which you can try to answer in the class itself is, I naught by I, is this ratio going to be greater than 1, less than 1, or less than 1 always? Which of these three inequalities make sense? Well, the point is that I naught is the one that is absorbed, right? I naught is the one that is absorbed, and I is the intensity of the emitted light. Okay, right? So, or we can include one more thing, greater than or equal to 1. What is the answer? Well, we know that we've been always talking about the absorption of light by molecules, right? And what happens in a molecular cloud? In a molecular cloud, it is the molecules which are responsible for the absorption of light. So when molecules absorb light, they either emit back everything, right? In which case, the intensity of the light emitted is going to be exactly 1. That is not even part of the option, okay, right? Or, what can happen is that the light absorbed is always going to be greater than the amount of light absorbed is going to be greater than the amount of light emitted, right? Are we good with this, right? So therefore, it can never be less than 1 or less than or equal to 1. It is always either greater than 1 or greater than or equal to 1. In the case, where there is 100% emission, such as in the black body radiation, right? Your I naught by I, right, is always going to be equal to 1. In other cases, it is going to be greater than 1. All right. So considering both the cases, mathematically, this inequality always holds good. Are we good, right? This is just, some common sense and logic-based idea. Okay. Now, astronomers, over many decades of experiments, right, based on, understanding like how much intensity is emitted by a star, right, have experimentally found that your I naught, or like your I by I naught, okay, right, is equal to 10 to the power minus some constant times L. Okay, right? This is an empirical relationship. Empirical meaning what? It is not modeled on any theory or any physical assumption. It is just based on pure experiment. Okay, right? Now, if you think about it, this fellow I by I naught is of course going to be unitless because both are intensities. This is a number on the RHS. Overall, it should be unitless, 10 to the power something. And your K is going to be what? Your K is therefore going to be, is what is called as an extinction coefficient. Okay, right? Your K is called as extinction coefficient and it has per length, right? Per length. And in the context of astrochemistry, this per length term could also be expressed as per light year or per parsec. Okay, right? So it could be expressed either as per light year or per parsec. And L, of course, is actually going to be the dimension of the molecular cloud. Okay, so this is going to be the dimension of the molecular cloud, or the astral source which emits the light, okay, which absorbs and emits light. Now, isn't it a powerful relationship? If you notice this expression right here, right? This expression right here, let's call it expression I. Okay, right? Is very powerful because based on this, right? Based on this, one can calibrate and compute this the LHS of this expression I by some experiments. Similarly, your K can also be obtained. What experiments I'm not telling you, okay? But knowing this and this, you can actually calculate the dimensions of the molecular clouds. Okay, right? Please note this. This is very important. Okay, right? So please understand that this term on the LHS can be obtained experimentally, right? Similarly, this can also be computed or like obtained experimentally. And so overall, using this formula, you can calculate how big is a molecular cloud. Isn't that a very a cool idea in astrochemistry. Now we therefore can predict, being right here on Earth, right, without even any theoretical advance or anything, by using an empirical relationship. We can predict the size of molecular clouds, the size and dimensions of molecular clouds, which are way, way, way far from us, all the way in the ISM. Okay, to put it better, this is going to be page 4, and note that in equation I, the LHS could be obtained from experiment. And how, I did not tell you, okay, right? Probably will not tell in this course. Probably, you may learn more about it in a course dedicated to astronomy itself, okay, right? So, how? Not for this course. And in the RHS, your K, or the extinction coefficient, can also be, obtained from experiments. And the L to be calculated based on equation I. Let us look at an example of it. Okay, I'll delete this page now. So now that we have seen this expression I, I'll give you a specific example. Now let's say that your I by I naught value, okay, right? I by I naught value at a given lambda, okay, from for any molecular cloud. By the way, this is an example. Okay, this is an example to illustrate how this formula is used to calculate the dimensions of the molecular cloud. Okay, so let's say the I by I naught for any given lambda for a given molecular cloud happens to be around, the value in this example is 0.24. Okay, right, 0.24. And also, let's say that your constant coefficient K, right, that is computed as 0.0032 per parsec. Okay, right? So I've told you that this can also be obtained from experiment. And of course, how? We're not going to discuss in this course. Did not tell. Did boy will not tell. Okay, so this is going to be per parsecs. Okay, right? And so therefore, the question is to find the diameter of the molecular cloud. Okay, so this is an example which we can solve based on the formula given here. Okay, let's solve it. So we simply substitute the formulae, and we know that my I by I naught is going to be 0.24, is going to be 10 to the power minus 0.0032 L, right? Which means that my L is going to be obtained by what? You have to take the logarithms, right? That is going to be given by negative log of the base 10, because this is the, it is raised to the power 10 here. So 0.024 divided by the 0.032. I'm sorry, there's a small typo in this number here. This should be 0.032. That's what I've written in the example. Okay, so this should be 0.032. And you can either use a scientific calculator or the Clark's table, whatever, like your logarithm chart, to find out that this is going to be approximately 194 parsec. Recall that your parsec is a measure of length. Okay, right? Can you convert it into light years? And this, in terms of light years, is going to be what? Based on, recall, we had it's approximately 3 times, right? somewhere around close to 3. So can you do the exact math? It turns out to be approximately 631 light years. Okay, right. So what does this calculation illustrate to you? It illustrates just how big, a molecular cloud can be, right? And this also tells you how giant our galaxies are, how vast, and then how sparse, because we're talking about number densities of the order of 10 to the power 3 or 10 to the power 6 or something like that in such a vast space, okay, right? So therefore, this huge magnitude of the diameter of a molecular cloud can be computed using a very simple formula, which is not even based on any theory or anything like that. It is completely obtained purely based on experiments. So therefore, so far, right, in this lecture, I was just telling you the power of empirical measurements, along with all the theoretical ideas and the theory-based hypotheses. Empirical ideas can also be very powerful in determining some seemingly unobtainable quantities, such as, for example, the dimensions or length of a molecular cloud. Okay. In fact, the same expression, right, is used in laboratory physics and chemistry also. Just that this K over there, right, is further expanded in terms of the concentration of the molecules present, and also you have some constant called as epsilon, which is the molar extinction coefficient. Okay, but in astronomy and astrochemistry and astrophysics, a slightly varied version of that particular law is used. Do you know the name of that law I'm referring to? Yes, it's called as the Bohr-Lambert or the Beer-Lambert's law. Right? So it is the same empirical law, but only that the extinction coefficient, right, is expressed in terms of per length. That is like per light year or per parsec in the astro sciences. That is in astronomy and astrophysics. Okay, right? All right. So what did we see so far? We were looking into an empirical way of understanding the intensities, right? The intensities of spectral lights, and from that, how various parameters, such as, for example, the dimensions of a molecular cloud, right, could be computed. Now, we actually go back to what did we all start, say, 4 or 5 lectures ago. We started all this discussion with the interaction of light with matter. Okay, right? So it's kind of now time to, go back and touch base to continue therein. Okay. Okay. So we are now going back to, after having looked into the empirical description of intensities of spectral lines, and now that gives us information about, various parameters associated in space, such as, for example, the dimensions of molecular cloud. We'll now go back to, so we are going back to the interaction of light with matter. Okay, right? So what all did we look into so far? We have looked into absorption, right? And we also looked into spontaneous emission and stimulated emission. But is that all that happens when light interacts with matter? And as soon as we saw all of these 3 aspects, right, we then went on to discuss various aspects, such as the Einstein coefficients and how that is connected with intensities, and how this is connected with the transition moment, the dipole, etc. And we discussed about selection rules, the gross selection rules, the forbidden versus allowed transitions, etc. And as part of it, we also were talking for quite some time about, for the last 10-15 minutes, about empirically obtained intensities and their use also. So, but this is where our discussion began, right? Overall. Now my question is this all that happens when light interacts with matter? What other things can you think of when light interacts with matter? So some of the other things that happen as light interacts with matter are obviously, right? You can think about what? Imagine light, right, is falling on me. How do you see me? You see me because light is getting reflected, right? Of course. So you talk about reflection. What else? Well, the minute I say reflection, right, it takes you back to your high school, and then you talk about refraction, and you talk about, like, therefore dispersion, right, which is the splitting of light, etc., etc. All of these happen, right? Now all these things, right, all these things together, all of these together, right, reflection, refraction, dispersion, etc., etc., are just subsets of a more general phenomenon called as scattering. Right? I mean, consider reflection. What is reflection? Light rays, right, just bounce upon some surface and then boom, right? They go back at a specific angle, right? The angle of incidence is equal to angle of reflection, and all those optics laws shall follow, right? Now, that reflection, right, is a particular form of what is called as scattering. That is, when light falls on, just gets attached to some matter, right? What happens is light just scatters away, right? The English word scatter mean to just, not in any, without any emphasis on any direction, just to fall back on all directions, right? In general. That is what the English word scatter means, right? Okay. So, if scattering occurs, like with a specific angle, depending on the nature of the matter with which it's interacting, you get reflection, you get refraction, etc., etc. Okay. So the general phenomenon, the other general phenomenon, besides absorption, spontaneous emission, and stimulated emission, is that when light interacts with matter, scattering also happens. This is extremely important in astrochemistry. Okay. We may not go into excruciating details of light scattering. Okay, right? But we should just know that there are two types of scattering which are relevant to astrochemistry. It is that elastic scattering and inelastic scattering. Okay, right? Now, what happens, in elastic scattering? In elastic scattering, what happens is that the incident photon, right? The incident photon which interacts with matter, right? The photon's energy, the kinetic energy of the photon and its momentum, both are preserved. Okay, right? So please note that in elastic scattering, I'll just print elastic. Okay, we are anyways talking about scattering. So in elastic scattering, the photons from the light, that is, okay, right, their kinetic energy and momentum, I'm just generally writing it as P, okay, right, are both the same before and after interaction. Now see, elastic scattering, keeps happening all along in the interstellar medium because there are going to be lots of particles, right? When I say particles, we're talking about stuff like cosmic rays, proton rays, etc., etc. And of course, when scattering happens, it could happen in an elastic or inelastic way. So when it so happens that when like the photons from light, right, even after colliding with matter, that is like interacting with matter, if the kinetic energy and momentum are still the same, right, it has tremendous implications. It has tremendous implications in astrochemistry. For example, it has been postulated, okay, right? It has been postulated and it's kind of experimentally verified in high energy particle physics, okay, right? That this elastic scattering, right, is in fact responsible for the creation of, chirality in space. Okay, right? So don't think that, just because something the collision is elastic, that is the interaction of after the interaction of a photon from light with matter, because both the kinetic energy and momentum are conserved, right? Don't assume that it is not useful in astrochemistry. It in fact is extremely useful, and we kind of know from high energy particle physics, I'm of course not going to go into the details, right, that this elastic scattering of light, especially the elastic collision of proton-proton rays in particular, okay, right, are kind of responsible for the creation of chirality itself, okay, right. So this is a topic which we shall briefly touch upon when we discuss the idea of chemistry in space. After we're in the module of detecting molecules in space, right, and that's where we learn about all the spectroscopy, the types of processes, etc. Once we go back to the chemistry in space, we'll get to talk about the chirality in space. Okay, note this point. But for this chirality in space, elastic scattering is an important process. Okay, elastic scattering and elastic collision. All right. So this is elastic collision, or elastic collision and scattering of light when it interacts with matter. Now, what else can happen is, in elastic scattering, what happens is that the kinetic energy of the photon changes, whereas the momentum, momentum may or may not remain the same, okay, right? So I'll just put it this way. So the kinetic energy of the photon changes. Now this is extremely important. This point, right? This point, that the kinetic energy of the photon, the photon, not proton, photon changes before and after interacting with matter. This process of inelastic scattering is extremely critical in astrochemistry, in the sense that, imagine a photon interacting with some molecule. Now, while the kinetic energy changes, the energy of the molecule or matter has also changed, therefore, right? Because the net energy is always going to be conserved, okay, right? So now based on this idea, what is going to happen is that the energy of the photon is getting transferred to a molecule. As a result, the state of the molecule changes. The molecule could either go from ground state to excited state, or if enough energy is transferred, the molecule may transform into some other molecule itself altogether, okay, right? So inelastic scattering is of paramount significance, is of extreme importance, right? Paramount significance in the formation of new molecules in space. Because I've written this reasonably fast, okay, I mean, I'll tell it again. So inelastic scattering is of paramount significance in the formation of new molecules in space via photon induced reactions, by photon driven reactions. What I've written here is photon driven reactions. I mean, it's in the bottom part. So photon driven RXN reactions, okay, right? So along with absorption, spontaneous emission, and stimulated emission, when light interacts with matter, two other things also happen, which is elastic scattering and inelastic scattering. Of course, all your reflection, refraction, dispersion, blah, blah, they're all a subset of scattering. So we need not worry more about them, okay? But both elastic scattering and inelastic scattering are exceedingly important in astrochemistry, because it is inelastic scattering that actually, can lead to a lot of new molecules from existing molecules, okay? And the elastic scattering, they're also very important in the sense that elastic scattering, right, has been shown to be responsible for the origin of various phenomena, such as, for example, chirality. I haven't gone to the details, but when we discuss, the origin of chirality, which is a separate module in the same course, I shall be, briefly touching upon some aspects of elastic scattering. Okay, so in this lecture, we were discussing about the significance of empirically using ideas in astrochemistry, such as, for example, the simple empirical law that I by I naught is 10 to the power minus KL, using which the dimensions of molecular clouds, etc., could be computed, right? We saw that. And followed by that, I was just telling you about two other ideas that happen when light interacts with matter. That is like elastic and inelastic scattering, telling you that every other form of change that happens to light, such as reflection, refraction, etc., are all nothing but subsets of scattering. Okay. So on that note, we shall be seeing each other in the next lecture. Thank you so much.